Welcome to lecture 5.2. We're going to be looking at exponential functions and graphs today. Very important area, specifically because almost everything we do financially, from the interest you pay on your credit card, to your car loan, to your house loan, to the interest that you earn on investments, this is all done with exponential functions. So it's a very powerful. Today we're going to learn how to graph exponential equations and exponential functions, and we're going to solve some applied problems involving their exponential functions and graphs. So we're pretty familiar with exponents, the little number that goes above a number to the right, as we can see here. Let me pull my pointer out here. But the difference with an exponential function is that instead of a number like 2 to the power of 3 or x to the power of x squared or something like that, an exponential function now has the variable in the exponent. An exponential function, notice, has the x or the variable in the exponent. Before, the x was the base, which we're labeling a here. So x is a variable real number. Our bases will always be positive. They can't be 0 and they can't be 1 because it makes no sense, right? 1 to any power is still going to be 1. 1 squared is 1, 1 cubed is 1, etc. So it doesn't really give us a variable function. And so an exponential function has the variable in the exponent. The base is a positive number, and the base needs to be positive in order to avoid the complex numbers that would occur by taking even roots of negative numbers. And that'll be explained a little bit more as we go along. The following are examples of exponential functions: 2 to the power of x, 1/2 to the power of x, and 3.57 to the power of x. We could also have an expression in the exponent. For example, we could have 2 to the power of x plus 2, where x plus 2 is all in the exponent. To graph an exponential function, follow the following steps. Compute some function values and list the results in a table. This is actually what we do all along. Pick some x values, put them into your formula, and then find the y values, plot the points, and connect them in a smooth curve. Be sure to plot enough points to determine how steeply the curve rises. And this is what we get the term exponential growth, or something is growing exponentially, meaning it's growing faster and faster, or it's shrinking exponentially. So let's look at our first example here. Graph the function y equals f of x, which is just notation, equals 2 to the power of x. So we find some, we pick some values of x. We've picked positive and negative 1, 2, 3, and 0. We plug it in, so we get 2 to the power of 0 is 1, 2 to the first power is 2, 2 squared is 4, 2 cubed is 8. Okay? 2 to the negative 1 is 1 over 2, 2 to the negative 2 is 1 over 2 squared, or 1/4, and 2 to the negative 3 is 1 over 2 cubed, or 1/8. If we graph this, we can see here are all the values. So as we go from left to right, we can see that the graph is growing steeper and steeper, which means that the growth is getting faster and faster. As x increases, y increases also without bound. As x decreases, as we go to the left, y decreases, getting closer and closer to 0. So as x goes to negative infinity, we have y is going to 0. The x-axis, or the line y equals 0, is a horizontal asymptote. As the x inputs decrease, the curve gets closer and closer to this line, but does not cross it. This is an example of what we call exponential growth, because as we go from left to right, we can see that this function is growing faster and faster. How do we know that? Because the slope is getting steeper and steeper. It's getting more and more straight up and down. If we look at another function, y equals f of x equals 1/2 to the x power. If we first rewrite this so that it looks similar to the last model, notice that 1/2 x is the same as, well, 1/2 is 2 to the power of negative 1, right? Because that's a negative exponent means we take the reciprocal here. So we get 2 to the negative 1 raised to the power of x, which is same thing as 2 to the raised to the power of negative x. Okay? Well, think about that. This tells us the graph is a reflection of the graph y equals 2 to the x power across the y-axis. Selected points we have in our table here. And so we can see how the points are reflective across the x. So we get the opposite value of x here. So when it's 1, 2, we get negative 1, 2, 2, 4. Negative 1, 1/2 becomes 1, 1/2. And so instead of growing from left to right, we have the function decreasing or shrinking or decaying from left to right. So as x increases, the function values decrease, the y values decrease, getting closer and closer to 0. The x-axis, y equals 0, is again the horizontal asymptote. As x decreases, the function values increase without bounds. So as x gets smaller or goes towards the negative direction, the function is getting higher. Okay, this is what we call exponential decay, that as we go from left to right, we see that the values, or the y values, or the functional values, are getting smaller and smaller. So let's look at that exponential decay and exponential growth in terms of some functions. Here we have a group of exponential decay. You'll notice first that the bases on the absolute value of the base is less than 1. What this means is that they are fractional values between 0 and 1. Okay? As the fraction gets smaller, the slope gets steeper. Okay? So as the fraction gets larger, I say the graph gets fatter. It gets, kind of levels out a little bit. But as the fractions get smaller, the graph gets taller or steeper or grows faster. Smaller the fraction, the faster the growth. The larger the fraction, the fatter the graph, or the slower the growth. Okay? On the right here we have a group of exponential growth models. And as we can see here, that the larger the base, as the base grows, the steeper the curve, the function, the y value is growing faster as well. And that makes sense, right? 2 squared is 4, but 4 squared is 16. So the y value would be growing much quicker. Okay. Here again, we see that the base is a number greater than 1, a positive number greater than 1. All our bases are positive, but here we have any values greater than 1. So we don't have the fractional values from 0 to 1. All right. Another way to think about these typically is that exponential decay happens when exponents are negative. And remember that when we had 1/2 to the x, we could write that as 2 to the negative x. So here we have 1/4 to the x. This would be the same as 4 to the negative x. Okay? And exponential growth typically happens when the exponents are positive. Okay? 4 to the x, etc. All right? Let's look at a graph of y equals 2 to the x minus 2. This is actually a graph of y equals 2 to the x shifted to the right by 2 units in the positive direction because it's inside the function. Okay, but we can always pick some x values, plot them, and then just see what's going on. So if I have x equals -1, I get -1 minus 2, which is -3. 2 to the -3 is 1 over 2 cubed, or 1/8, and you can see that there. I'm not going to go through all these values, but you can see them there. And here's our graph, okay? And this is indeed 2 to the power of x shifted to the right 2 units. When we have a plus or minus in the exponent, this is a vertical shift to the left or the right, and it goes in the opposite direction. So minus numbers go to the right, and plus 2 would go to the left. 5 minus 0.5x. Okay, well remember this is 5 minus 2 to the negative x power if we rewrite 0.5 is 1/2 x, and then rewrite 1/2 to the power of x as 2 to the negative 1 to the power of x, or 2 to the negative x. When we have a constant outside of the function, this is an up or down translation. So this is a graph, a reflection of the graph of y equals 2 to the x across the y-axis, followed by a reflection across the x-axis, and then shifted up 5 units. Okay, it's across both of the, x and y, because we have the negative x in the exponent, and we have a -2 here as well. Okay, but again, we can easily just plug in values into our calculator or look at the table and then see what graph comes up. Okay, so here we're shifted up by 5, we're flipped across x, we're flipped across y, and we can see the graph shape there. So let's look at an application problem. Again, a big application is around finances. The amount of money, A, which you have at some future date, to which a principal is the original amount that you put into an account. A principal can also be the original amount you borrow to buy a house or a car, etc. Will grow to after t years. Time is always in years in financial problems. At an interest rate r, and we convert interest rates into decimal forms by moving the decimal 2 to the left. Compounded n times per year is given by the formula future amount equals principal times 1 plus interest rate over number of compound periods. This whole parenthesis quantity raised to the power of compound periods times the number of years. Okay. Suppose that $100,000 is invested at 6.5% interest compounded semi-annually. Let's look at these numbers and see how they relate to the formula. The $100,000 is what we put in initially. Okay, so that is our p-value. It's called principal in financial, or present value, what you start off with. It's invested at 6.5%. So our r value would be the 6.5% converted to a decimal, which would be 0.065. Compounded semi-annually, that's our n value. Semi-annual, semi means half a year. So this is compounded every 6 months, or 2 times per year. So our n is going to be equal to 2. And for our first question, it says find a function for the amount at which the investment grows after 2 years with these specific input values. And so we just plug in the values. Again, 100,000 for p, 0.065 for r, and 2 for n, and we get this formula here. Our question B was to find the amount of money in the account after 0, 4, 8, and 10 years. The easiest thing to do here is use your y equals function in your calculator. Y equals 100,000 times parenthesis 1.0325 parenthesis raised to the power of 2t. And then go to the table function and go over and see where x equals 0, 4, 8, and 10, and then you can find these values. Okay, but when t equals 0, that's just when we're putting money into the account, and so it makes sense that when we put money into the account, when t equals 0, it's just the money that we initially invested. And then you can see here how quickly that will grow at an interest rate of 6.5, which is a very nice interest rate. So within 10 years, you've almost doubled your money at this 6.5 interest rate. And then lastly, we'll graph the function, and you have your calculator to do all of this. Okay. The big thing here is if you're asked to find multiple values using a formula, it's really in your best interest to plug that into the y equals function in your calculator and then go to the table function. Otherwise, when you're entering each of these individually in your calculator, it's easy to miss a parenthesis or to do some other data entry mistake and then get one or more of these answers wrong. Whereas if you put the formula in, you can check the formula before you look at the table to find the values. There is a number called E. This is Euler's, it's not Euler's constant. I thought it was, but it's not Euler's constant, but it's Euler's, it's a number that represents a base for many exponential functions that occur in science, in nature, and in finances. This is Leonard Euler, a Swiss mathematician from the 1700s. And you got to think about this guy. This Euler's number is an irrational number, which is kind of like pi, which means it's a decimal that doesn't repeat and doesn't end. Now, he calculated this. He noticed this pattern in exponential growth in finances and in nature. One of the most common uses is, or two common uses. One is the Richter scale to measure earthquakes. The other is carbon dating. Carbon decays at a certain specific exponential rate, and if you figure out how much is missing, then you can figure out how long that fossil, how old the fossil is, or the bone, or whatever. So he was a Swiss mathematician. To me, it's amazing to think that, exponents are not logical math. It's not, easy to see how 2 cubed is 8 or whatever, to see patterns there. And he didn't have a TI-84 like you do, and yet he was able to figure out that this constant base, this base was constant in a lot of exponential growth that was happening across different fields of study, from engineering to mathematics to finance to biology, etc. So he is one of the most prolific mathematicians, although most people don't know of him outside of the field of math, because he published more than almost anyone else. But to me, it's just amazing that he's from the 1700s and had this insight without the technology and tools that we have. So let's just look at these Euler bases. E. Find each value of e to the power of x to 4 decimal places. You'll notice on your calculator to the left you have an e to the x key. So just go ahead and do e cubed, e to the negative 0.023, e squared, and e to the power of 1. Okay. This is just using your calculator. I'm not going to go through these values, but you can check yourself, and it's a good idea to go ahead and try these because you're going to have to do some problems, and you don't want to make simple mistakes as you don't know how to use the e to the x button. Graph f of x equals e to the x and g of x equals e to the negative x. Use the calculator and enter y1 equals e to the x and y2 equals e to the negative x, and then enter some numbers for x. So here we have a little table again that we can see what's going on e to the x and e to the negative x. This would be in your calculator. You can look at it yourself if you're using your calculator. And here we have our original function, f of x equals e to the x. And here we have g of x equals e to the negative x. And again, we can see that when the exponent is positive, we have exponential growth. And when the exponent is negative, we have exponential decay. And what you may not see from these two graphs is that they are a reflection of each other across the y-axis. Okay, they are just simply a reflection across the y. If I superimpose g on f, you'd see it go right here. And so I would plug these into your calculator, and then you can see it on one graph. You can see both of those functions, which is a good thing. Okay. Now we're just going to look at a couple examples. I'm going to walk through these pretty quickly. Again, you have your calculator, so there's not a lot of calculations you have to do. It's really just using your calculator and finding the graph. So the graph of f of x of e to the x plus 3, because the plus 3 is happening in the exponent, then we're going to go 3 units to the left. Remember, we go the opposite direction. Since it's plus 3, we're going to go 3 units in the negative direction. Again, we can find x values and find y values by simply using our calculator. And so we have this function here, which is e to the x translated to the left 3 units. Here we have e to the negative 0.5x. The graph of this is a horizontal stretching, so it's being stretched wider. It's being made fatter on the graph of y of e to the x. Well, now, why is it getting fatter? Because look, we're multiplying by a fraction. It's happening inside the exponent, inside the function, so that's a horizontal impact. And it's because it's a fraction, remember that the graph gets fatter or it grows slower. Okay, And because it's negative, it's being reflected across the y-axis. Remember that if it's positive, you get growth. If it's negative, it flips across the y-axis and you get decay. So again, we can see a table of value, and then we can see that this is indeed flipped across and it's getting fatter. It's not growing quite as fast as e to the x or e to the negative x. Here we have a graph of 1 minus e to the negative 2x. So first of all, we have a 1 outside, so this is telling us that we're going to go up 1. And then we've got a double reflection here, reflecting across x, reflecting across y. And the growth is going to be faster because we're multiplying by a factor of 2. Okay? So the graph of 1 minus is a horizontal shrinking. Now it's getting skinnier, which means it's growing faster. Okay? Because the multiplier is a number greater than 1, not a fraction between 0 and 1. Okay? It's followed by a reflection across the y-axis. That's our negative here, and that's our negative here across y. And because it's minus, this is also going across the x-axis. Followed by the translation up, because it's a positive 1, a vertical translation of 1. Again, we can simply draw create some x values and create a table, and then see a graph there. So this is just giving you some insight into what's happening with exponential growth, exponential decay, how it's used in some functions. Specifically, we did a financial problem, and then seeing what's happening is how the graphs translate when we add constants into the formula, or we add constants and multipliers in the exponential function. All right, this is the end of 5.2. Hopefully that worked out well, and reach out if you need any help.